Here we have 28. The water in a reservoir behind a dam drops from initial height H0 above a turbine to produce hydroelectricity at time t is equal to t and h is equal to 0. The graph shows the variation with time t of the height of the water above the turbine. Which of the following is a measure? Now this is an important word there, measure. We've used that in terms of temperature also. It doesn't mean that it's equal to, but it usually is proportional, give a proportional value to the maximum theoretical electrical power available. Now we know that power is equal to work over time. We also know that this work, this energy that can come, is coming from mgh, and so that's over time. So this h0 is very important because that really gives you an idea of the total energy available. And then the slope of the graph is the rate that the h is decreasing. So that will give you a rate with how much energy is used. So it would actually be A is the correct answer here, because the steepness of the slope is how quickly this h is decreasing, and therefore how quickly the energy is being used, and therefore an indication of the power of the turbine. Good. Going on to the next question here. So going on to this one here. We have here each square meter of the sun's surface emits s joules per second. The radius of the sun is r, and the sun is a mean distance big R, capital R, from the earth. Which of the following gives the solar power incident per unit area of the top layer of the earth's atmosphere? Okay, so in looking at this, we need to know firstly what is the total power that is being emitted from the sun. So this is the sun. It's got a, as it says, it's got a radius r, and therefore the total area of the sun, the area would equal 4 pi r squared. You need to remember that formula, the surface area of a sphere. So the power that's going to be emitted therefore will be 4 pi r squared s, because for every, this will be in meters squared, and this is s joules for every meter squared. So that will give you the total power. Now that, obviously now I've drawn the sun very big, but anyway, just imagine here you've got the earth, and that's a certain distance big R away. Now that's also a gigantic sphere. Now all that energy is going to be filled into all that sphere. So what is that total surface area? Well, we'd have to divide this by 4 pi r squared, and that would be, this is the total power that's emitted, and this is the total surface area that it's going on to. So obviously those will cancel. We can simplify this down, and we would see that B looks like a good solution for 29, because here we would see that it's R over R squared S. So we're going to have B. And then moving on to our final question here. And here we're going to need to use some of our formulas that we'll look at. So it says in the diagram shows a simple climate model for Earth. The temperature of the ground is given as Tg, and the assumed rate to radiate as a black body. The temperature of the atmosphere is Ta and has an emissivity of epsilon E. In the model, the intensity radiated from the ground equals the intensity radiated from the atmosphere towards the ground. What is the ratio of Tg over TA. This all seems very complicated. So what we need to do is we need to look firstly, we're going to be using this formula over here because this I here is the intensity and here you have power, and we're going to be using these two formulas over here. Now this is for a black body where you're getting a perfect emission, and this is for a partial black body where you're getting your emissivity there. So we can see there that our power that is being radiated, it says here that the intensity radiated from the ground equals the intensity radiated from our atmosphere. So we have power is equal to IA, and that is for the power for the ground and also the power for the atmosphere. Now if we take obviously that our area is going to be the same, we can assume that our intensity is the same. That is equal to sigma A, and here we're going to have Tg to the 4, and here we're going to have sigma. Now we've got our emissivity here, because now this is for the atmosphere, we have to use this formula, the atmosphere, and for the Earth we have to use this formula because we are told that it's a perfect emitter. So we have there is equal to A T A to the 4. So this cancels, this cancels, this cancels, this cancels. This will all equal 1. So we're going to get that our E is equal to Tg over Ta to the 4. So obviously I'm going to have to find this over here. I'm going to have to do that to a quarter to cancel that out, and I will get this one over here, which will be C, e to the 1/4. Alright, so it's very important that you know all your terms, what all your terms mean in these.